In the last video, we looked at a two-sample comparison of means where we assumed that the variances in the two groups were the same. In this video, we're going to look at a slight variation of that analysis where we're unable to make that assumption. So the data I'm going to look at here, it concerns numbers of Chinook salmon that were released and surviving in streams that either did have or did not have brook trout. And so just like in the last video, I'm going to take my categorical variable and turn it into a factor so that I can put the levels in the order that I want them to be in. And then in this case, instead of histograms, I'm going to actually look at strip charts because I don't have nearly as much data as I had in the horned lizard example, and histograms aren't very meaningful when you have very small sample sizes. So instead I'm going to look at a strip chart, and that shows me a little more clearly what's going on with this data set when we have such a small sample size. So here we go. The proportion that are surviving in each of 12 streams is the response variable in this case, and then my predictor variable or my treatment variable is whether brook trout are present in the streams or absent from the streams. And so we can see the actual values here are the circles. So in the treatment group where brook trout are present, and the treatment group where brook trout are absent, and the bars here are showing me a sample mean for each group, and then I've got error bars on here as well, going out one standard error from the sample mean. And then I can also summarize the data, and we can look at the sample mean in the brook trout present group is 0.194, and the sample mean in the absent group is 0.235. So what's going on here is that we are thinking that the brook trout, the presence of the brook trout, is having an adverse impact on the proportion of Chinook salmon that are surviving in these streams. So the proportion that are surviving when the brook trout are not present in the stream is a little bit higher than the proportion of Chinook salmon surviving if there are brook trout there. Okay, so in other words, the brook trout are bad for the Chinook salmon. Brook trout are an introduced species, and the Chinook salmon are native. Okay, so we can see a difference in the means in the samples, but of course our question of interest is this sufficient evidence of a difference in the population means? Okay, that's what we're really interested in. So ordinarily we would say, okay, let's do the analysis that we did in the last video. We'll do a confidence interval, we'll do a hypothesis test, and that will give us an answer to the question. But remember, what we did in the last video was to do a test that relied on the assumption that the variances in the two groups were the same. Here, the sample spread in the two groups is vastly different. So I'm not sure that making the assumption that the population variances are the same would be reasonable. The rule of thumb that we talked about briefly in the last video was if one of the sample standard deviations was at least 3 times bigger than the other sample standard deviation, then we might not be able to assume that the population variances are the same. And in this case, here's the sample standard deviation in the absent group, and it's more than 3 times bigger than the sample standard deviation in the present group. So we're in a situation here where we're going to have to use something called the Welch's Approximate T Test. So to do that, we can calculate a confidence interval and do a hypothesis test just like we did before, but we're going to have to slightly alter some of the calculations that we do. So let's just quickly run through them. So let's do the confidence interval first. So the pieces we need are the sample means, the sample standard deviations, the sample sizes, and then this time the standard error calculation. It's a little bit different from the standard error calculation in the last video where we did assume the group variances were the same. So this calculation is a little bit different, and then the calculation for the degrees of freedom is very different. It's kind of complicated. So if you're doing this by hand, it's very easy to screw this up and make a mistake. The other interesting thing here is that we usually think of degrees of freedom as being a whole number, whereas when you do this calculation, you don't get a whole number. So what some people do here is they round this number down. Okay, and that's the approach that the book takes. But it turns out that R doesn't care if the degrees of freedom for a t-distribution is not a whole number. It calculates it anyway. So what I'm going to do in this video is I'm going to leave this number unrounded. Okay, so the rest is the same as it always is when we're calculating a confidence interval. Figure out what alpha is. So for a 95% confidence interval, alpha is 0.05. Figure out the critical value, and then the lower bound of the confidence interval is given by the difference in the sample means minus the critical value times the standard error, and the upper bound is given by the difference in the sample means plus the critical value times the standard error. Okay, so we're 95% confident that the difference in the population means is from minus 0.15 up to 0.07. Interesting. So this interval goes from a negative number to a positive number. So in other words, the value 0 is inside this interval. So what that is telling us is that there's not really very compelling evidence here of a difference in the population means. A difference in the population means of 0 is a plausible value here. And if that was the case, what we're saying is that the population mean for the present group could be the same as the population mean for the absent group. We can't really rule that out. What about a hypothesis test? So, given the conclusions I just was able to draw from the confidence interval, if we do a hypothesis test now, what do you think the outcome is going to be? Are we going to end up rejecting the null hypothesis that the population means are the same in favor of the alternative that they're different? Or are we going to end up not being able to reject that null hypothesis that the population means are the same? Hopefully, in your head, you're thinking, well, given what you just said, it seems that we're not going to be able to reject the null hypothesis here. We're going to end up with a relatively large p-value. Okay, so if you're thinking that, that's great, because that's what ends up happening. But let's run through the steps just to confirm that that is indeed what will happen. First step, state the null and the alternative hypotheses. So the null hypothesis is that the mean proportion of Chinook salmon surviving is the same in streams with and without brook trout. So in other words, the population means are the same. And the alternative hypothesis is that the mean proportion of Chinook surviving is different between streams with and without brook trout. So in other words, the population means are different. That's step 1. Step 2, calculate the test statistic. So we set the null value for the mean to be 0, the mean difference really, and then calculate the test statistic. So it comes to minus 0.93. I'll just show you that. Minus 0.93. And then the p-value, there's the calculation, and it comes to 0.39. So that's steps 1, 2, and 3. Step 4 is decision and conclusion. Decision rule, reject the null hypothesis in favor of the alternative if the p-value is less than 0.05, the significance level. Otherwise, we cannot reject the null hypothesis. So in this case, this p-value is not less than 0.05, so we cannot reject the null hypothesis. So be a little bit careful here. That does not mean that we're concluding the population means are the same. We're concluding that we cannot rule that out. Okay, so subtle difference here. We're not accepting the null hypothesis. We are not rejecting it. Okay, so that's how to do all that with long, complicated hand calculations. Alternatively, once you're comfortable with what's going on here, we can use the t.test function. So here's my formula that I'm using. Remember this tilde again, we talked about that before in the last video. So here's my response variable, here's my predictor variable, and this time I have to set var.equal as false, because we're not assuming equal variances in the populations in this case. And if you set this argument as false, let's actually look this up so we can see. T.test, this argument here, let's read what it says. So this is a logical variable indicating whether to treat the two variances as being equal. If true, then the pooled variance is used to estimate the variance. So that's what we did in the last video. Otherwise, if it's false, we end up doing Welch's t-test. Sometimes this goes by the name of Satterthwaite. Okay. Alright, so let's run that, and here we get all the information that we calculated by hand earlier. There's the test statistic, there's the degrees of freedom, there's the p-value, the two-tailed p-value, and then here's the 95% confidence interval. Okay, so that is how to do a comparison of a two-sample comparison of means when we're not assuming that the variances in the two groups are the same. And so we end up using Welch's approximate t-test to do that analysis.